Hello, how are you? I hope you're doing good. I'm also doing great. Welcome to today's lesson. I hope you're going to learn something. Kindly sit tight and be ready to learn on the design of a simple U-step. Today we are dealing with the design of a simple staircase. And a staircase is a structural element that is used to access areas of different elevations. For instance, if you have a story building with more than one floor vertically, you are going to use a staircase to move from the ground floor to the first, to the second, up to the roof. And a stair is also used sometimes to access things that are in a higher elevation. Sometimes you could be having like a water tank, you need to move from one floor to another, or you need to move from the ground to just some elevation high. So in that case, we normally use a staircase. And a staircase uses I can say it's a more complex ladder. It works like a ladder because a ladder enables you move from a lower elevation to a higher elevation. So the staircase we're going to study today is a simple U staircase, and a simple U staircase derives its name from the shape of the staircase because you have a landing here, you have another landing here, and then these sections at the center are called flights. When you see this circle, it means you are starting climbing from here. You go all the way, you get to the first landing. At the first landing, you still proceed, you continue climbing. Therefore, this is the first flight, this is the second flight. Then once you reach here, you get to the second landing, and the level of the second landing is normally the level of the floor where you're headed, be it a first floor or the floor above, or a mezzanine floor, or whichever place you're headed. The second landing is normally at the same level, so that once you have arrived at the landing, you can now proceed to access whichever utility you are looking for at that elevation. When you look at my staircase, it is a simple floor plan, and it is dimensioned with the width of my steps, which we normally call the treads, is 300 mm wide, and the height of those steps we will see it when we look at the section. And you can see for both flights the width is the same. When you look at also these dimensions, it shows that we have a wall or a beam on this side, and another here, and another here, and another right here. But once you also study our staircase, you realize that because our flights are slanting, therefore it is not really necessary to have the beam flat, straight, and then you slant it at this section, and then you also have it horizontal. We normally design the staircase as a one-way spanning slab, such that we cut it at this section, and then we design this part where the flight is slanting, but this section is flat and this is flat. And therefore, it is taking all its loads to this beam and all its loads on this side to this beam. Therefore, it is only distributing its load along one axis. And this enables us to assume that there is no support here, and the stair is not distributing its load to any support at this point. So this beam that has been placed here, or this element, is just to show the boundary of our staircase. And in this case, the most important beams that we need to consider when designing a staircase are these ones. However, sometimes you have a support at this point that is supporting your staircase. Therefore, you're supposed to distribute the load to all supports that are surrounding it. But it is safe to design a staircase as a one-way a spanning slab, so that it spans only along one axis. And you can see the width of my staircase is 1200 mm wide, and that is the width of my flight. And the other flight, it's also the same. And once you look at these tapes, they look exactly the same. Therefore, they are also the same in number. And the distance between one flight to the next, just that void that we normally have at the center, is 100 mm wide. Therefore, I think this is enough from this, and then of course these dimensions are 200, and we could assume also these beams are 200 millimeters wide, though sometimes you could have them wider depending on your structure and what you're designing and its utility. Also, you look at these dimensions, it shows that you have the first landing has a dimension of 1.15 meters, and then the flight has a horizontal dimension of 2.7 meters. Kindly do not assume that this is the slant dimension of the flight. This is the horizontal dimension because we are viewing it from the plan view. And then the second landing has a dimension of 1.4 meters. Here is a simple section of how the staircase looks like. And as said, we will see the riser, that is the height of the step, that is 150 millimeters high. And then the width of the step, which we normally call the tread, is 300 millimeters wide or long. And this is the same for this flight and this flight. And in this case, we are going to assume that our flights are of the same dimension. We can break this down further. You can look at the difference in elevation from this floor to an upper floor, and the distance in the difference in elevation is 3 meters. And once you subdivide that into two, then you're going to have 1.5 meters and 1.5 meters difference. I'm going to subdivide that further because we've said we design this staircase as a one-way spanning slab. Therefore, I'm going to cut it at this section and consider this part so that I can design for this part, and these, since they are uniform, I can replicate the same here. Sometimes one flight is longer than the other. It could be good practice to design both so that you provide reinforcement required for both, but sometimes you just design for the longer or for the bigger dimension so that that acts as your critical element and you can replicate it to the one with a smaller dimension. So once you have a staircase with uh, the flights of different magnitudes, then you could design the most critical one and replicate the reinforcement and sizes and all that to the one that is not so critical. So I have cut my staircase at this section, therefore I'm going to design this bit because this bit is getting its supports from the beam that we have here and the other beam that we have here, which is also happening for this section. There are some staircases. You find that I have this stair and then I have this flight. I get to my first landing, and then sometimes there could be a shorter flight here of say let's say 3 or 4 steps. And then I get to another landing, then I proceed to the other flight. So sometimes these steps might confuse somebody, and you might want to design the staircase as having its support from this end. If there is nothing supporting it, if you design like that, you'll be making a mistake. In that case, you're supposed to still treat it as a one-way spanning slab, cut it at that section, and then get the total loading and determine the way it is going to load this beam at this edge and the beam on the other landing. So sometimes if we have steps at this section, those steps might confuse you, but use them to get the volume of concrete, the density, using the density, and you can get the loading. Then you can distribute that loading to your supports. But having said that, is just analyze your structure, look at all the supports, consider them in your design. Because sometimes if you have steps here, you could be having a wall or a beam that is carrying your this landing part. Therefore, you can distribute part of the loading to this structure here, such that you are going to assume that this structure is distributing its load to these supports along this axis. And then for this one, it also distributes some loading to this axis, and sometimes probably at this section it could be cantilevered. So you are still going to distribute it to this side and then this load you still use it distribute it along this axis. But just consider the supports you have, they are the ones to guide you on how to distribute your load. And you can see that I have broken it down. The first landing measures 1.15 long, and the flight measures 2.7 meters horizontally, and then the second flight landing measures 1.4. You can see there is a dimension of 150 here that I have not talked about. This is called the waist of the staircase. This is what we normally use to get the effective depth of the staircase. And from earlier lessons, we learned that effective depth is the dimension from the topmost surface of your element to the center of the main reinforcement, um, providing the reinforcement that is countering tension or compression or torsion or any other stresses at that point. So it is the distance from the topmost surface to the center of the main reinforcement providing strength at that place, and that specifically works for such elements. In a cantilever, it is the other way around because tension is high on the upper side. Therefore, for a cantilever, it is the distance from the bottom to the center of the main reinforcement at the top. But for our case, it is the distance from the top of our element to the center of the main reinforcement at the bottom. Therefore, you can see that my waist is 150 millimeters, then my riser is 150 millimeters also. My thread or my step is 300 millimeter long, and you can also see the slabs at the landings are 150 millimeters thick. Now we start our design, having looked at how the staircase looks like. The height of our risers is 150, we have seen that, it's right here. The width of our threads is 300. The waist of the staircase is 150, as you can observe here. And the effective depth can now be obtained because we have the waist. Effective depth, we've said, is the distance from the top to the center of the main reinforcement at the bottom. So that means we take 150, we subtract the bottom cover, and I'm assuming a cover of 20, and we subtract half the bar dimension, assuming I'm going to use a main bar of 12 millimeters, therefore I'm going to get 6. So 150 subtract 26, I'm going to have 124 millimeters as my effective depth. The slope length, which is also important, this dimension here, it's important because we have to use it to determine the volume and therefore the density and the loading of concrete at that section. So that is obtained using the normal Pythagoras theorem, where we take the horizontal dimension, which is 2.7, and we take the vertical dimension, which is 1.5, and 2.7 squared, add 1.5 squared and get their square root. That will give you 3.089, which is approximately 3.1 meters long. Therefore, my slope length is 3.1 meters. Now let us determine the loading of our staircase. The first thing to consider is we are designing a staircase and we are going to consider 1 meter width of the staircase. Why do we consider that? 1 meter width is going to help us because any number multiplied by 1 is just that number. So we are going to use 1 so that the width is not going to really give us trouble. But remember, the width of our staircase is 1200 millimeters wide. So we are just using 1 meter so that it makes it easier for calculations, and also when we design slabs per meter squared. So that is why we are considering this 1 meter. Now, weight of the waist at this section, I'm just considering the flight. So my waist is 150 millimeters deep, and then the length is 3.1 as we had obtained from this rule of hypotenuse. So 3.1 you multiply by 0.15, which is the depth, and this is going to give me my sectional area. Then once, if I multiply by 1, because we've said we are considering 1 meter width, therefore I'm going to still retain that. And this gives me my volume of concrete at that section. I also consider the uh, uh, additional area of concrete on top of my waste. Once I draw a slanting line from this tip to this tip, you will realize that I will be having my line will be touching all these points here, which means I'm going to remain with small triangles on top of my waste. Excuse me. I don't know whether we're still recording. Yes, we're still recording. Thank you. So the area is a rectangular area. Therefore, I'm going to determine that area. It is a half multiplied by this dimension, which is 300 multiplied by 150. So a half multiplied by 0.3, that is in meters, and multiplied by 0.15. And then the steps are 10 in number. So you multiply by 10 so that you can get the total cross-sectional area, which when you multiply 1, it's still the volume of the concrete at that section. So once you add the weight of the stair, the weight of the waste of the stair, and the additional steps, which we have called staircase in this case, you will sum them up and multiply by the density of concrete. That will give you 16.56 kilonewtons, and this is the loading of your concrete at this section. Then you proceed to determine the weight of the landing. The weight of the landing is simple. You get the total dimension of the landing, and in this case we are going to add this side. This is 1.4 and add 1.15, and you multiply by the depth of the concrete and the density to give you 9.18 kilonewtons. Therefore you sum all, both of these, then you get 25.74 kilonewtons. Therefore this is the dead load of your staircase. For the live load, once you consider the British standard for loadings, you will realize that for a residential structure, staircase live load is supposed to be 3.0 kilonewton per meter squared. However, as the designer, sometimes you can't change this value to even use 4, 4.5, or even 2.5. So it depends with what you're considering in your design, whether there could be a change of utility of your structure in future, and where the structure is located, the construction procedures, and all that. So this is determined by the designer, but 3 is a recommended value from the British standard for loadings. And then you take that loading and then you multiply the plan area. This is where most people make mistakes, because they assume that even if this area is slanting, my live load is going to act on this entire section. No, live loads are acting on a plan area. Therefore, I'm going to take my 1.15, and then I get the plan dimension from here to here, not the slanting, because live loads are acting on the treads, on the steps, and they are not acting on the vertical components, which are the risers. Therefore, since they are acting on the steps, you can sum up the dimension of all steps. And since these steps are 9, I think 300 by 9 will give you 2700. So 2700 is what you will use for your live load, and not 3100. And also for the landing, you use 1400. So if you sum them up and you multiply that by 3, you're going to get 15.75 kilonewton per meter squared. Therefore, using clause 2.4.3.1.1 and table 2.1, I'm able to use the factors of a load modification, and I'm going to obtain my ultimate load. My partial factors are 1.4. This is for my dead loads or permanent actions, as the Eurocode would call it, and 1.6 for the live loads or the variable actions, as Eurocode would call it. So I sum them up and then I get a load of 61.236 kilonewtons. Therefore, this is the load I'm going to use in the design of my staircase. Next, I assume a simply supported structure. Remember, we said we are going to design this staircase as a one-way spanning slab. And a slab is basically a series of beams, or slab and beam design procedures are always the same because they are horizontal members that provide support. So I'm going to, whether I'm going to interchangeably use the word staircase, slab, and beam, but I'll be meaning the same thing. And once you look here, this is the end support, and I'm going to assume that this is an end support and I'm not having continuity on this side. Therefore, there is no balancing of moments from this side, and I'm just having a simply supported staircase. And I assumed that for my design. Sometimes you could also assume, not assume, sometimes you could consider the continuity on this side and factor it as you're analyzing your staircase. So if I assume that my supports are simply supported and that the loading I'm having is uniformly distributed, I'm going to use the formula FL over 8 to get my maximum bending moment. F being the total load, which is 61.236, you multiply it by the total dimension. The total dimension is a sum of this, which is 5.25. Then you divide by that by 8 to give you 40.186 kilonewton meters. Therefore, this is the moment I'm going to design against. And I'm going to proceed. This is obtained in clause 3.4.4.4 of the code. I think we can open that. This is the code we use for the design of structural elements of reinforced concrete. And it is structural use of concrete part 1. This is the British Standard 8110, the part 1, the 1997 version. And this is how the cover page looks like. But I'm going to proceed to 3.4.4. This is 3.5. Let me increase this. Yeah, I'm at 3.4 right here. 3.4.4 is the design resistance moment of beams. Remember I said we are going to use beams, slabs, and staircase interchangeably in this case. Sometimes I could also use this design ultimate bending moments and shear forces, and I could use this table to get my moments instead of using this formula. But since this formula is simple and it's simplifying my work, that is why I prefer that. So my main point is the K that you are seeing here, this one. So for the K, the following questions, which are based on simplified stress block of figure 3.3, are also applicable to flanged beams where the neutral axis lies within the flange. And K prime is equals to 0.156, where redistribution does not exceed 10%. This implies a limitation of the neutral axis to d over 2, or K could also be obtained by this formula where redistribution exceeds 10%. And since our redistribution does not exceed 10%, we are going to take our K factorial as 0.156. And the K that we are supposed to obtain from this formula is supposed to be less than that. If our K value is greater than that, then we are going to provide compression reinforcement for that element. Therefore, you take M over BD squared FCU, you feed all the parameters into the formula. If the K is less than that, then if the K is less than K prime, then there is no need for compression reinforcement. If the K is greater than that, then there is need. So we are considering 0.156. Let's go back. Our K was determined from that. This is the moment, and then 25 is the class of concrete used, 1000 is the breadth, and this is the effective depth. This gives me a K of 0.1045. Look at this. This is 0.156. So 0.156 is greater than 0.1045. Therefore, there is no compression reinforcement required for this element. Once I've obtained that and there is no compression reinforcement required, I proceed to use this K to determine my lever arm Z. And once I feed the K into the formula, I'm supposed to determine my lever arm Z, and I think I should go back to the code so that we can see that. If K is less than or equal to K factorial, compression reinforcement is not required. And the code provides for how you provide for compression reinforcement if it is required. But for today, our element is not required, and I think we need to handle an element where we will be providing compression reinforcement. Therefore, because this is true, we proceed and use this formula. But it comes with a clause that, but it should not be greater than 0.95D. Therefore, our lever arm should be our value or 0.95D, whichever is less. So if I feed this into the formula, I get 0.866D, and this is less than 0.95D. Therefore, I'm going to use 0.866D as my lever. And this is what I will feed into the formula. Now, because I have all parameters in determination of the area of steel required, and this is tension for tension reinforcement. So M is my moment, and then 0.95 is the factor that we use there. For Fy, it is 460. And you multiply it by the Z, which is the lever arm, to get 856 millimeters squared per meter. But I would like to say something about this 460. Let's go back to table 3.1. Table 3.1 is in the British Code. I think it should be next up there, right here. This is what we use for characteristic strength of reinforcement. Let's read this clause. Characteristic strength of reinforcements are given in BS 4449, BS 4482, and BS 4483, and are as shown in table 3.1 here. Design may be based on the appropriate characteristic strength. So, appropriate characteristic strength. In my country, manufacturers provide reinforcement that is more than 500 Newton per millimeter squared. Therefore, it is expedient to assume that my specific characteristic strength is minimum is 500. Therefore, I could replace this with 500, and once I'm doing the design calculations, or a lower value if necessary to reduce deflection or control cracking. The reason why I'm stating this is recently I did a design. I forwarded my design to the local authorities for approval in some county in my country, Kenya. And one of the engineers was insisting that we need to use 460 because this is what the code has stated. But the code does not just limit us to 460. The code gives us the ability to examine our situation and use the appropriate characteristic strength or use a lower value if necessary to reduce deflection and control cracking. Therefore, this is up to the designer to carry out. You can even carry out tests of your reinforcement in a laboratory before you do design. You can go to the manufacturer, get sample steel elements, and go and carry out tests in a laboratory to determine the characteristic strength of your reinforcement so that you can use the appropriate values for design. Or sometimes you can get the certificate of manufacturer because all these elements have been certified by the Kenya Bureau of Standards, you can get the certificate of the manufacturer and you can see the proposed characteristic strength of your steel. But that notwithstanding, it is good to use 460, but also apply this appropriate characteristic strength that you have at the moment. For that, you feed all that information into the formula and you get an area of steel required of 856 millimeters squared per meter. And if we provide 25 millimeter bars spaced at 125 millimeters, we're going to have an area of steel of 904 millimeters squared per meter. And therefore, this is greater than the required, which makes our design okay at this point. Therefore, this reinforcement is able to cater for tension in the structure. Next, we determine deflection. And deflection is a very important check to determine an staircase because it is based on the depth of your waist that you selected, the waist and the landing. If the depth is small, then your element is going to fail in deflection. So you are going to have an element that is safe in terms of provision of reinforcement, but it's going to fail in deflection and it can excessively deflect to the point it can crack and lose its utility. This is obtained from 3.4.6, which we can quickly rush there. 3.4.6. This is 3.8, 3.5, right here. 3.4.6 deflection of beams. So this is what is going to guide us in this deflection. But I would like to read 3.4.6.3. The basic span of effective depth ratios for beams are given in table 3.9, which are here. These are based on limiting the total deflection to span over 250. And this should normally ensure that the part of the deflection occurring after construction of finishes and partitions will be limited to either span over 500 or 20 millimeter, whichever is lesser. That is what we are supposed to limit our deflection to. Therefore, I could say that our deflection is supposed to be less than 20 millimeters for spans up to 10 meters. For values of BW over B, this is the breadth, greater than 0.3, linear interpolation between the values given in table 3.9 for rectangular section and for flanged beams with BW over B of 0.3 may be used. So sometimes we could interpolate between these values to get what is required. And table 3.9 is the basic span over effective depth ratio for rectangular or flanged beams, and this is what we're going to use also for our staircase. Here you consider the support conditions, and the support conditions for our case, our staircase is not cantilevered. Our staircase, we assumed it to be simply supported. And sometimes you could be having a staircase that is continuous. So for continuous, you use 26 because we are considering a rectangular section. For simply supported, you use 20. And if you have flanged beams, therefore these are the values you're going to use. To go back to our work, now basic span over effective depth, we have agreed we are going to use 20. These are for simply supported. Therefore, you use this formula. Let's go back to the manual. The formula for the design is here. Let's read this table 3.10 modification factor for tension reinforcement. So this one, when you're designing for deflection, you can apply the modification, you apply the modification factor for tension reinforcement, and this will give you the factor, this modification factor we call MF. This is what you will come and multiply with the value of 20 we found from the other side to get the limiting span over effective depth. And from the code, you can see modification factor is given by this big formula here, and it is supposed to be less than or equal to 2.0 from equation 7. So you could also read this from the table by if you get m over bd squared and you have your fy as 460, you could read the values from the table. But where m in this our formula is the design ultimate moment at the center of the span, or for a cantilever at the support. So this is where the moments are greatest. But for our case, since it's simply supported, our maximum moment is at the center. Note 2. The design surface stress in the tension reinforcement in a member may be estimated from this equation. So the design surface stress, which we normally call Fs, is determined by 2 Fy As required over 3 As provided, multiplied by 1 over this our beta B. And I think let's see what beta B is. Beta B is the ratio of the moment at the section after redistribution over the moment at the section before redistribution from the respective maximum moments diagram. So you take the moment after you've done redistribution, the moments before redistribution, and you get your value of beta B. In this case, I'm going to assume our structure, we are not redistributing anything. Therefore, I take this conservatively as 1 because the moment will be the same before and after distribution because we are not distributing anything. So using equation 8, I'm able to get the design surface stress in the tension reinforcement. Note 3 states that for a continuous beam, if the percentage of redistribution is not known, but the design ultimate moment at mid-span is obviously the same as or greater than the elastic ultimate moment, the stress Fs in this table may be taken as 2 over 3 multiplied by the characteristic strength of my concrete. Therefore, since our structure is not continuous, note 3 does not apply for our structure. And you can also see the modification factors for compression reinforcement. Remember, these were for tension. Compression reinforcement are here, and the equations are right there. So having stated that, we can go back. I've shown you how to get the Fs, and I've also shown you how to get the modification factor, which is 0.993. Therefore, you can take the limiting span over effective depth, which we said should be 20, and once we subject it to the modification factor, it becomes 19.86 millimeters. Therefore, this is supposed to be the maximum deflection or the limiting deflection at that section. If I consider the actual span of effective depth, my span is 5250, my depth is 124, I'm going to have 42.34 millimeters. Therefore, this tells me that I'm having an issue because 42.34 is greater than 19.86. This calls for a redesign because my effective depth is not sufficient. But let me recheck this because we committed a mistake. Or sometimes it's good to carry out these checks so that they enable you understand how your structure is behaving. So I'm checking out this to find out whether we got the right value there. 477 subtract 290.4 divide that by the previous answer, 0.443, then you add to 0.55, 0.993. Yes, the value is correct. So since the actual span over effective depth is greater than the limiting span, therefore my structure is going to fail against deflection. So what am I supposed to do? Increase the waist of my staircase. And for the landings, increase the depth of the landing. This calls for a redesign of the structure because our structure has failed in deflection. Let's proceed and redesign it. We assume a depth of 200. For this staircase, you can try and assume a depth of 175 and redo the design, and you will find that it is still insufficient. And you could try this 200. And effective depth, we already stated how to get it. For this case, we found it as 174 millimeter. You take the total depth, you subtract the bottom cover and subtract half the size of the main reinforcement, and this gives you 174 millimeters. For the loading, it is the same as when this was 150, but now this dimension changes from 0.15 to 0.2. So for the steps, the height is still 150. That is why we are still retaining that. And you get your value there. This was 0.15, it changes to 0.2. I've already explained this up there. So you use the same way, but now substituted it with 200, and it's going to give you an ultimate load of 70.728 kilonewtons, which is greater than the previous ultimate load of 61.236 kilonewtons. So using this ultimate load, I can now get my moment, which is 46.42 from the formula. And I explained this because we assumed simply supported ends. And then I determine my K. My K is less than 0. I think 156. Therefore, we don't need compression reinforcement here. And I determine my lever arm Z, which is 0.93D, and it's lesser than 0.95. Therefore, I'm going to adopt 0.93D. I'm going very fast because I've already dealt with this up there. And the area of steel required, I've explained how to get it, and this gives you 656.434. And therefore, initially I had provided 12 millimeter bars spaced at 125, but I'm going to provide 12 millimeters bars spaced at 150. And this will give me 753 millimeter squared per meter. And this is therefore sufficient. But let's still carry out the deflection check because this is what failed. And once you carry out this, the moment was 46.42. Then the effective depth changed to 174. You get this m over bd squared as 1.533. And then the fact this fs is 267.34 because I take my area required and I divide by the area provided, I multiply by the characteristic strength of my steel, and multiply by this 2/3 factor, and I get 267.34. So I take this and these values, I feed them into my modification factor formula. They'll give me a modification factor of 1.268. This is what I multiply to the factor 20 for simply supported to get 25.36 millimeters. Therefore, this is the limiting deflection. When I check the actual deflection, I take the entire span divided by the effective depth. I'm going to get 30.17 millimeters. This is still greater than the limiting span of effective depth. Therefore, we have faced the same challenge we faced earlier on. And the actual span over depth is greater than the limiting span over depth. Therefore, our staircase is still not okay in deflection. I intentionally used this example for this lesson so that you can see and appreciate the issue of depth in staircases. And once you have designed many staircases and you are able to tell which kind of depth can be safe against deflection. And sometimes you can even change the way you are supporting your staircase before you start designing, because prior you can look at the spans and the loads and preliminarily determine whether it is going to be safe. Here, another option I have an option of still continuing to increase the depth. Option number 2 is to alter the reinforcement I've provided, because if I alter reinforcement, it is going to affect this factor here, this 753. Assuming I'm using 16 millimeter bars spaced at, let's say, 150 millimeters center to center, that is going to give me a value of 1340 here. Therefore, I can feed that here, redesign this, and then find out whether after modifying increasing my reinforcement and looking for the modification factor. Obviously, these will be greater, because if I use a bigger reinforcement, these will be greater, and these will increase, and it could fail, or it could make the design or the construction very expensive, because now you have increased reinforcement. Therefore, another option could be to reconsider my supports. Remember, my landing are supported at the end. I could consider introducing a beam at this section and another beam at this section, such that this landing is supported by the beam. So what I'm going to design majorly for is the flight. And then the landing, I can design it like a normal staircase. And then if I put a beam here and I put another beam here, I'm going to consider this staircase as a continuous supported staircase, which will increase my factor to 26, because it will be continuous instead of 20. Also, I could just introduce a support on one section only. Instead of doing it here, I can just introduce a beam at this point, which is going to just limit my design to that section. And that is what I did for this case. I introduced a support there, and this makes it continuous for that side and simply supported for that side. Therefore, reduce the span of the staircase by introducing a support beam at the landing and flight junction to reduce the span. Sometimes it's not possible, because maybe this beam does not have columns or any support structures that are going to where it is going to distribute its load to, or sometimes it is not aesthetically pleasing and the architect does not want to have a beam there. So you will be forced to redesign your staircase to reduce the loading on that staircase by introducing a support. You could introduce a support here so that it has some cantilever element on the staircase, and it's going to make your design easier and help you not use a very deep staircase. Also, you can still continue to increase the waist from 200. You can proceed to 250, then proceed to 300. But that is going to make the structure very heavy and uneconomical for no reason. You can also consider using light structures like expandable polystyrene elements, or you could use hollow blocks and such structures for your structure. So having said that, for our case, we introduced a beam at that section, and then we repeated the entire procedure, but now the span shifts from being 5 point something, it was 5.25, and it becomes 2.7 plus 1.15, and that is 3.85. So you come out, you do the math again, you determine your loadings, the formula is still the same, but the dimension has reduced. You get an ultimate load of 47.46 kilonewtons, and you can see reducing my span helps me reduce the total loading from this landing and helps me reduce the total span. Therefore, my ultimate loading is way lesser. And in all the considerations we made, this was the most economical, introducing a beam at that section. Now, assuming simply supported ends, remember this end is not simply supported, but I'm assuming that for the design of this, so that I'm not having hogging moments at this point because of the um, how we call it, because of the continuity at this span. The reason why I'm assuming this is because for my structure there was another beam here, therefore I'm going to have a slab of 1.4 meters wide and then a staircase. Therefore I'm not expecting excessive bending moments at the support, so my maximum bending moments are going to be those at the center. But sometimes you could draw your bending moment diagram, get the maximum, and design for that throughout your structure. So you proceed with the same procedure, close 3.4.4.4. You can use that to determine the lever arm, and which was 0.93. But you can look, after introducing a beam here, the span was short, and I tried using a depth of 150, because now we have reduced the spans, the loads have reduced. Therefore, we can try using 150. If it still fails, we can now proceed to increase the depth. So using that, we proceeded, and the maximum moment was 22.84, and this has significantly reduced by almost half, because initially we had the bending moments of around 40, this is 46.42, and earlier on it was around 40.186. So the bending moments reduced significantly to 22.84. And once you use the moment, you can also come up with that Z, and you determine the area of steel required, which was 453.22 millimeters squared per meter. This is very it is not very high as opposed to the ones we obtained earlier on. So you provide 12 millimeter bars spaced at 150 millimeters center to center. And that is 753 millimeters squared per meter. Therefore, let's still carry out the deflection check. The basic span of effective depth, we assumed it to be 20, and then I determined all these parameters right there as you can see it, and this gave me a modification factor of 1.57. When I multiply 1.57 by 20, I get a limiting a deflection of 31.41 vis-a-vis the actual deflection of 31.04. Therefore, even if these values are close, the actual span that is going to happen in my structure is less than the limiting span. Therefore, finally, my structure is okay in deflection, and my structure has passed that deflection check. Remember, we have done this 3 times. Whoa, it's a sigh of relief. I intentionally took us through this so that we can appreciate that preliminary design is very essential when you're designing a structure. And sometimes you're forced to design a structure 2 or 3 times so that it can pass a certain check. This is not in vain, because it is necessary so that your structure does not fail against deflection. But once you get experienced in this, when you're doing your preliminary design, you're able to size your element depending on your spans and your loadings to certain sizes that will rarely fail when you're carrying out your checks. From there, because we have passed the deflection check, we proceed to the second check, which is the cracking check. It is in clause 3.12.11.2.7. Let's look at the cracking check, 3.12.11. Cracking check. I'm going step by step so that we understand these things. 3.12. What is that? This 3.5. 3.11 right there, 3.12 right here. So it was 3.12 point what? 0.11.2.7. Where is that? 3.12.8, 0.10, 0.11. Yeah. This is spacing of reinforcement, and it is 0.11, 0.2, 0.7. That is where our concern is. 0.2, 0.7 right here. This is when we are designing for cracking. In no case should the clear spacing between bars exceed the lesser of 3 times the effective depth or 750. This is what they mean. My effective depth in this case is finally 124 because I took a staircase of 150 millimeter thick waist. So 3 multiplied by 124 is 372. Therefore, the maximum spacing of my reinforcement is not supposed to be the greater value of either 372 or 750 millimeters. So because 372 is the lesser value, that is the one we use. And my spacing was 150. That was my minimum maximum spacing, which is less than 372. Therefore, it is okay against cracking. But we can proceed. In addition, unless crack widths are checked by direct calculation, the following rules will ensure adequate control of cracking for slabs subjected to normal internal and external environments. A. No further check is required on pass spacing if either of these three is met. For grade 250 steel, the slab depth is not more than 250 millimeters. Our grade was not 250, so condition 1 does not hold. Grade 460 steel is used and the slab depth does not exceed 200 millimeters. Did we use for 460 grade steel? Yes. Did the slab depth exceed 200? No. We finally settled on 150. Therefore, condition 2 holds. Since it holds, there are no further checks required for bar spacing in terms of cracking. 3 states that the reinforcement percentage is less than 0.3% where the parameters of the formula are there, and where none of the conditions of 1 or 2 and 3 apply, the bar spacing should be limited to the values given in table 3.28. 3.28, which is here. But since our condition 2 fits into our structure, therefore there is no need to proceed with carrying out the cracking check. And our structure is therefore safe against cracking. The next step is to determine the distribution steel, because remember the steel we have determined is the main steel in our element. So we are now to proceed and determine the distribution steel. Distribution steel in this case is the steel that will be used to hold the main reinforcement in position, because this a slab, as I would call it, is one-way spanning on only that one direction. So for the distribution steel, table 3.25 governs that you use 0.13 BH over 100. 3.25. Let's get to the table very fast. We are almost finishing. 3.25. 3.25 right there. We are talking about tension reinforcement. Our structure did not require compression reinforcement, so this one is not applicable. So for tension reinforcement, our section is rectangular section. In solid slabs, this minimum should be provided in both directions. So our minimum percentage of reinforcement is 0.13. So you take the definition of percentage that, and you apply the minimum percentage, and you're going to get what you require. So if you apply that into the formula, you're going to get 260 millimeters squared per meter. If we provide 10 millimeter bars spaced at 150, center to center, they'll give us an area of steel of 393 millimeters squared per meter. Therefore, this is safe against that minimum reinforcement. So we provide 10 millimeter bars spaced at 150 millimeters center to center. Having designed everything, now our checks, our cracking and deflection checks are okay. We have installed distribution steel and we have also installed the main steel. We can now proceed and do a sketch of the reinforcement details. And when you look at the sketch, this sketch starts at a point, let's call this the ground floor, and it proceeds to the first floor. Sometimes at this starting point, it could be starting inside a beam. Therefore, the reinforcement at that section is governed by where it is starting. So you have to get the total loading, you get the loading it is exerting on that beam, and distribute it there and find the reinforcement that is sufficient to be carried by the beam. But in our case, it was carried by a concrete foundation on the ground. So that is why the foundation has three 12 millimeter bars spaced at 200 millimeter center to center. Sometimes if the soils are very bad and the bearing capacity is poor, you have to increase this and design it appropriately. And now let's examine this. I think I need to increase it so that we can see. For the first flight, we have the main reinforcement. This is a top reinforcement. We have opted 9 to 12 at 150. Remember, we provided 12 millimeter bars spaced at 150. And once you take a distance of a width of 1200 millimeter wide, you divide by 150. You subtract the cover on both sides, assuming a cover of 20. So I'm going to have 1200 subtract 40, 20 on either side. That is 1160, and divide by 150. I'm going to have 7.7 plus 1 because I need to add the extra bar. That is 8.7. Therefore, 9 bars are sufficient. So I have 9 top 1 bars. And for bottom bars, I have 9 to 12 bars spaced at 150. And these are binded by distribution steel of 10 millimeter bars, still spaced at 150, both at the top and at the bottom. And these values you're seeing here, these are the barcodes that you can now refer to your, if you have a bar bending schedule, these barcodes are the ones that will show you how the bars will be bent, how they'll be cut, and they also help you to procure your reinforcement. And also remember, we introduced a beam as this section, so it's important you design this beam. Take the loading, distribute it to the beam, and also it is carrying the loading from the slab on the other side. So those two loadings will help you design that beam accordingly. That is where we have not provided reinforcement for this beam. And considering that we designed this as a uniform element like a beam, it means we have already designed for the reinforcement at this landing. Therefore, this reinforcement from the slab is the same reinforcement that goes to the staircase. So it's not supposed to be designed independently because we have already designed it together with the staircase. And it's supposed to be uniform. You can see 10 millimeter bars spaced at 200 B2 over T2. And if you ask what governs this is the area of steel required. Remember, we settled on the use of 150 for my distribution steel. But let's go back to our calculation. The minimum is supposed to be 260. Actually, if I use 150 for T10, the area of steel that I'll provide is 523, not 390. 393 is if my spacing is 200. Therefore, kindly, that is a mistake that we need to correct. So this, if we put 10 millimeter bars at 200, it is going to be safe because 10 millimeter 200 is what gives us 393. That is why you're seeing that. Though I prefer for slabs and staircases, I have uniform spacing for bars in both directions. That is why I would prefer we use 150 even if it will have a bigger area of steel provided, which is 500, normally 523. But for these sections, I could still return 150 or detail it to be 200. Therefore, I think that is it. You also detail your dimensions, the difference in elevations. This is also a detail you need to carefully consider and give it the way it's required. And I think that brings us to the end of the design of a staircase. The next stair that we will design, I think we need to do now a bit some complex one. We need to maybe design a helical stair so that because it has more than tension, and we will be designing for torsion reinforcement and all the problems that come once we use a helical staircase. So thank you for following through. I hope that this has been very beneficial and you have learned a lot. And proceed now. Once you're using your softwares, you're able to see, to check and find out whether you have fed in the right parameters and you have the right design. Therefore, thank you very much, and I hope that you have learned something. Please, if you've not subscribed, subscribe to our channel and text us, comment, and you can even inquire on things that are not clear so that in our next lessons we are able to make them clear. We also do construction. If you have a structure and you want a consultant, we also offer consultancy services, and we can construct structures based on the contracts that we get to with our clients. Our main office is in Nairobi, Kenya. Therefore, feel free to approach us for any project. Thank you very much. May the good Lord bless and keep you. Adios.